So in our previous class we have discussed about the clipper circuits, right? So how exactly a positive clipper or negative clipper circuit can be realized, right? So in today's class we will discuss something about the clamper circuits, right, using your operational amplifiers, right? Clamper circuits. So when I say clamper, you know the difference between the clippers and clampers. The clippers are used to clip off a certain portion of the input signal as per the requirement, and whereas the clamper circuits are basically to shift the waveform to a desired level, right? So whenever you want to shift the waveform from one level to another, you know what could be the reason behind it, right? So you will send the signal with clamped values, right, and again at the receiving end you will retrieve it back for the security reasons and all, right? So this is one important reason which is generally used in your communication technologies and all, adding certain level to the original signal, and at the receiving end you remove it and retrieve the original signal. That's how the things go as long as the clamper circuit is concerned, right? So now let us see, suppose if I have input signal something like this. So this is my input signal, okay. So this is V in. Now the same input signal, if I want to, please note that the 0 volt or the ground level has remained same here, right? So now if I want to shift this signal, let us say that this is the central point and the signal is shifted something like this, okay. So this is V naught, this is T. This is what you call as a simple positive clamper, right? So here basically I am going to add something to it, some DC signal. Let us say that this is the DC signal. So that results in the clamping of this particular waveform to this value. So could it be like this, or even you can have it on the other side also, depending upon your requirement, right? So it could be this way around also, okay, right? So this becomes your reference signal that time, right? So basically what you are going to do here is you are going to add a DC signal. That is very, very important, right? So predetermined DC signal is added. Basically in the clamping operation, what we do is we add some predetermined DC signal, right, and the output is clamped to desired voltage level. This is what happens as long as the clamper circuits are concerned, right? So and accordingly you have, you know, the positive clipper, positive clampers, right, or you have negative clampers, right, or you have something called as peak clampers, depending upon in what way you are going to shift the signal from its original value, right? Now whenever I say I add some DC signal, right, so probably you should you know, look back into one of the aspects which I have already told you in one of our earlier classes, the single polarity supply operational amplifiers, right? So in the single polarity supply operational amplifiers, can you recall the circuitry operation there, right? You have got an input capacitor, you have got an output capacitor. So if at all you are not using a dual power supply, instead you are using a single polarity power supply, what you will do is you will introduce a signal which is VCC by 2 to the inverting terminal, and whatever, sorry, non-inverting terminal, whatever the input signal is there, it will be added with certain DC level. It will be processed like that, it will be amplified like that, and again at the output stages, because of the presence of the capacitor, the DC level will be removed and you are going to get the required output. That serves a different purpose, right? So now whenever you want to add some DC level, the same philosophy or the same concept can be used here also in order to understand the working of a clamping circuit, right? So with that particular background, let us try to see one circuit, the peak clamper circuit. Let me write it as peak clamper circuit. So how exactly this circuit works and in what way we are going to realize the operation of this circuit, we will see now. Please note down the circuit diagram here for the peak clamper. You have operational amplifier, and very importantly, whenever you want to clamp the output voltage level, which component will be used? A special component here in this circuit for clamping purpose. Can anybody tell me?
Capacitor.
Yes, very good. The capacitor is a must because the voltage level is required to be changed there. So that is the reason why you require the capacitor. One second, I'll make some small changes here. Because we are discussing about the peak clamper, I have a diode here like this. Then this is connected here, and to this end I am connecting my load resistance. I hope all of you are noting down this circuit diagram. And here I have the capacitor, and of course here I have got my input supply V in. So this is the capacitor. This resistance serves some purpose which I will tell you later, and as long as the non-inverting terminal is concerned, I will have to, one second, use a reference voltage here. This also I will call it as plus VCC. This I will consider as R2, and this as R3, and this as load resistance RL, where you have got your output voltage V0, and this will be inverting terminal. This is my V in. All of you have copied down the circuit diagram?
Yes, sir.
Okay. Okay, now you see here, again you can recall the concept which I have just told you. an input signal to which you are going to add a DC here, right? So then you are going to get the clamped output, and of course this happens to be my V reference, and this is my V reference. This is a very important one, and this is a DC. V reference is DC, right? So now the output here, right, whatever you are going to have, the output is the combination, or it is a net result of AC input. So AC input at inverting terminal, correct or not? The AC input here is being applied at the inverting terminal, and DC input at non-inverting terminal. This is a very important point to be noted, right? So therefore both the AC as well as the DC inputs are to be analyzed separately here in this particular case. Okay, now let us try to have the analysis of this circuit, right? So let us have the analysis, how exactly the circuit works. Okay, here the reference voltage, V reference, whatever we are having, that is always positive in this particular case, right? So since V reference is positive, let me call this voltage as V naught dash as usual, right? So V reference is positive, right? So your V naught dash also has to be positive. I am trying to have the two analysis differently. One is the DC analysis, another is the AC analysis, right? So when your V naught dash is positive, so what happens to the diode? The diode is, yes,
Forward bias.
yes, very good. The diode is forward biased, right? Once the diode is forward biased, your feedback path is closed. So I use this feedback as FB, right? Feedback is closed, right? And the circuit now behaves as a voltage follower. This analysis we have already seen so many times, because the capacitor, whatever we are having, right? So it is, fortunately in this case, it is open for DC. The capacitor C is open for DC. This is the point to be noted. Otherwise, that capacitor will have its own role, right? It will act as a voltage follower. And for it to act as a voltage follower, what is the constraint here? What is the bottleneck? Can somebody tell me? For the circuit at this condition to act as a voltage follower, what is the constraint or what is the bottleneck? Voltage follower will not be having any resistance in series, is it not, in the feedback path? But you have got a resistance R1 here, right? Of course, this R1 serves a different purpose, and in design we have to consider the optimum value of R1 so that it does not prevent the circuit from operating as a voltage follower. That is one point to be kept at the back of your mind, right? So now your V naught is equals to V reference for the DC input. Your V naught is going to be equal to V reference, right? So when we have the DC input, okay, Now let us try to take the analysis from the point of view of AC. Input. So when I speak about the AC input, again I have to start taking from this point during the positive half cycle and during the negative half cycle. Same analysis comes into picture, right? Now let us start from the negative half cycle, right? So please look here. For we have to sometimes make the analysis as per our requirement here, right? Because this is a continuously changing input waveform, right? For V in at the inverting terminal, for V in at the inverting terminal during negative half cycle, during negative half cycle, right? So what happens to the diode D? D will now conduct, is it not? During the negative half cycle, the diode D conducts, because here this becomes positive, and the similar analysis what we have taken here, that holds good. Okay, so during negative half cycle, your diode D conducts. When the diode D conducts, when the diode D conducts, so you can see here the capacitor here. Okay, when the diode D starts conducting, right, the capacitor will be charged with this polarity until it reaches the voltage, say Vp. Okay, so the capacitor is charged to negative peak. The capacitor is charged to negative peak. So this is, say, Vp, the maximum value is Vp, and you know that during the positive half cycle, now I am taking the positive half cycle, during positive half cycle, during positive half cycle, so the capacitor, sorry, the diode will be D does not conduct. Okay, so therefore whatever the charge, so this kind of analysis you have already done according to me, right, when you have studied your analog electronic circuits, right? So during positive half cycle, since the diode D does not conduct, what happens? The charge, okay, across the capacitor is retained. This is very, very important. The charge or the voltage Vp across the capacitor is retained. Voltage across the capacitor is retained. So this is a very important point to be noted here, right? So now once the voltage across the capacitor C is retained, right, we will go to the next part of our analysis now, right? So your V naught, or you can write since Vp across the capacitor is in series, correct or not? So you can see here your Vp is in series with the input voltage, right? So that is in series with the positive peak, so Vp is in series with your positive peak, so your V naught will become twice Vp. V naught will become twice Vp, right? So the net output now, right? Because as I've already told you, I have to consider the effect of the AC input as well as the DC input at the non-inverting terminal separately. Because of the DC, what is the reference output voltage, that is because of the reference output voltage, what is because of the reference voltage, what is the output voltage that we have taken it to be V reference. And because of the AC, we have seen your V naught is equals to 2Vp. Let me call this as equation number 1 and this as equation number 2, right? So the net output is V reference plus 2Vp. V reference plus 2Vp. So this indicates the negative peak of Vp is at V reference. Now that is the reason why I did not draw the waveform here. Now the last sentence which I have written here should tell you how to draw the waveforms here. So this is how your peak clamper works, right? So now you must be understanding why it is called as the peak clamper, right? It will be shifted by a factor of your V reference, right? So now suppose if I have got the input here, let me see whether I can, yeah. So I will draw the waveforms here now. So this is my input signal, V in, okay, and the output I will take here with my reference remaining same, T, and let us say that this is my V reference. So here I will take some other reference, let there not be any confusion. So this is my V naught. So this is V reference, this is V reference, and this will be twice Vp. This is going to be twice Vp, and this is 0 volt line. Both are 0 volt line. This will be Vp. This is how you are going to get the shift in the output voltage. All of you please draw this. So now I think all the things are in a single window. Is the diagram clearly visible to all of you? Should I make it little big?
Clear. Visible, sir.
Okay, okay. All of you are using your laptops or mobile phones for viewing all these things. Laptops or desktops? Okay. So now in this example, or in this particular process, or in this particular working, right, we have taken care of the V reference, right? We have seen what is C, what is the role of C, right? We have seen what is the role of D. Of course, your resistance RL is the load resistance. And now R1 here, this is very important, right? So your R1, what for the R1 is used, can anybody tell me now? What for the R1 is used in this diagram. What is the purpose of using R1? See here, if you don't use R1 here, right, since we are using the capacitor, the discharge of the capacitor becomes very rapid and very high inrush current will flow into the inverting terminal. To prevent the quick discharge of the current, right, generally the value of R1 is used, right. You can just write down R1 is used to prevent the sudden discharge of the current. R1 is used to prevent sudden discharge of the current. So this is one point to be noted. And one more important point to be noted here, that is when you have the capacitor into picture, right, so the time constant also matters, right. So whatever the input you have, if you want to reproduce the input with the clamped value without any variation in the frequency and all, so you must satisfy one more condition, that is for precision clamping. For precision clamping, your C1 into RD should be much less than T by 2. This is one point to be noted, right. So this is the time constant C1 into RD. So that is, RD means the forward resistance. RD is the forward resistance of the diode. Okay, this is another condition to be satisfied, right, in order to make sure that the clamping is proper, right, and T of course is the time period of input signal. T is the time period of input signal. This is the working of your precision clamper circuit. Now if at all you want to, I hope this whatever you have taken, you are supposed to take down in this window is over.
Yes, sir.
Now suppose if you want to have so let us say that this is the input, this is V in. Now if you want to have the output something like this, this is my V reference. Okay, so this will be to Vp this side, this is your V naught, this is your Vp. So this indicates your negative peak clamper. Okay. So now if you want to have this operation, what is expected in your circuit to be changed? We have already seen these kind of things when we have discussed about the clipper circuits. What you will change here in this circuit, whatever you have taken in our previous slide. So your circuit would have a reference voltage which is negative minus VCC, yes, V reference, and the second change would be to have the diode in the opposite direction. These are the two changes that you are supposed to keep in mind in order to realize the working of the negative clamper. Right? This is R1, this is D, of course this is RL, V0, and this is V0 dash. This is R2, this is R3, minus plus. I have drawn the complete circuit. If you want, you can also write down. And of course, the similar expression what we have taken for your the positive clamper, the same thing holds good here also. So this is what is the negative peak clamper. V reference you can change as per your requirement, right? So if you keep the V reference 0, then you know what exactly happens as long as the output waveform is concerned. Is it clear to all of you? The positive and negative clampers. Let us look into one simple example on this. Though this example is simple, you can do it with different methods, right? And you may not get the same answer when you use different methods. I will tell you why. Okay, so let us go into the problem statement now. Design a clamper circuit. Design a clamper or design a circuit. Will not mention that it is a clamper circuit using Opamp to obtain the following waveforms. This is what is the problem statement, and the waveforms are given here. This is T, this is my V in, and this is 0 volt, this is 5 volt here. This is 5 volt. The input frequency is given to be 1 kilohertz. Frequency is given to be 1 kilohertz, and you have the output waveform something like this. This is T. This is V0. This is 2 volt, and this is 12 volt from 0. Okay, from 0. This is what is the requirement. Use the Opamp with a supply voltage of plus or minus 12 volts. Use the Opamp with a supply voltage of plus or minus 12 volts. Yeah. Now how do you proceed here? Again, let us try to draw the the circuit diagram. So always you should begin with drawing the circuit diagram. Even if it is redundant, doesn't matter. Please try to take the circuit diagram twice. That will give you a lot of practice. The capacitor, this is your V input signal, and this happens to be the diode. The diode direction is like this because it is positive clamper RL diode. So this is my VCC, this is also my VCC, which is plus 12 volt, this is minus 12 volt, so therefore this is plus 12 volt, this is my R1, this is C, so this is R2 and this is R3. My V reference in this case is known to be 2 volts. It is given in the problem, you can see. So this is minus, this is plus. This is what is the circuit, and to this circuit we have to now design the components C, R1, then R2, R3, select the diode and even the value of RL. So how do you proceed here? How do you proceed? See, whenever we have the operational amplifier, right? So if I1 is given, or at least if IB max is given, then probably we would have got the problem solution easily. Now nothing is mentioned here. Design a circuit using operational amplifier to obtain the following waveform. Use an operational amplifier with a supply of plus or minus 12 volts. That's all. Okay. So no information about IB max, no information about the value of your I1, right? Nor the information is given about the C. Okay. Suppose if you can recall the equation, right, previous, whenever we have the capacitor, right, so this capacitor, the selection of the capacitor strongly depends upon the input signal, the frequency and all. But fortunately in this problem we have been given the value of the frequency. Okay. So here basically when I take the input something like this, V in, so this delta V and delta T can be known to me. Am I right? Delta V and delta T can be known to me because delta V is already known to me. So from this point, okay, the input reaches its peak value of 5 volts in this much time, that is your delta T. So capital T you can find out, that is this one, T, which is equals to reciprocal of the frequency. Frequency is given to be 1 kilohertz, 1 divided by 1000, so this becomes 1 millisecond. So T by 2 also you can find out, so T by 2 is this much. Am I right or not? T by 2, all of you are able to get it. T by 2 is 0.5 millisecond, and your delta T, which is of course T by 4, looking at your input waveform, right? So delta T is T by 4, so it is 0.25 millisecond, and your delta V is equals to 5 volts. Correct or not? All of you agree with me or not? Delta V is 5 volt. So the input changes to 5 volt in a time period of 0.25 millisecond, which is related to the capacitor, right? So can you recall the equation which links all these things? The capacitor, your input current, and the rate of change of voltage somewhere earlier. Did we not see this equation? C is equals to I into delta T by delta V. C is equals to Q into V. This is the basic equation, right? Check whether this is correct or not, this equation whatever I have written. Q equals to C into V. Q equals to C into V. I into delta T is Q, correct or not? C into delta V, C into V equal to Q. So this was the equation somewhere earlier we had used, right? So now in this equation, I know the value of delta T, I know the value of delta V, but neither C nor I is known to me. Okay, so therefore in such cases the practice is to always assume the value of a standard capacitor. Assume the capacitance, right? So you can take either 0.1 microfarad or 0.01, that depends upon your requirement, but that should suit the input current of your operational amplifier that is selected also, right? So that's why there will be a lot of contradictions, right? So unless you have the catalogs with you, right, which operational amplifier you are selecting, right? So what is the input current and all, right? So generally you select the value of the standard capacitor, C equals to 0.01 microfarad or 0.1 microfarad, right? You can take it as 0.1 also, doesn't matter, but here I am taking the capacitance value equals to 0.01. So when I have taken the capacitance value of 0.01, so that should make me to use this equation and get the value of I. Okay, so your I is equals to C into delta V divided by delta T. So this is 0.01 microfarad into 5 divided by your delta T is 0.25 millisecond. Can somebody tell me the value of I? Calculate and tell me the value of
0.002 702 ampere.
Can you tell me it in milli or microampere? 200 microampere?
Yes, sir.
200 micro? Check, okay. I don't have the calculator with me right now. I 200 microampere if your answers are correct. Okay, so now let us say that this current is a very small current, so I don't this will be in terms of the bias current, right? So sudden inrush of this current should not spoil your operational amplifier. That is the reason I am using the value of R1. So V in is known to us, that is 5 volt, and the voltage across the capacitor also possibly maximum will be 5 volt, right? So the total voltage here, okay, would be maximum equal to 10 volts. 10 volts, correct or not? Okay, so now if you look at the biasing current, okay, we know the value of I, but we do not know what exactly is the biasing current. Okay, so here the potential maximum it could be 10 volts, for which we have to design the value of R1. So this happens to be my IB. Okay, generally your IB, as we have taken, it will be 100 times less than your current I. So what you can take here is I approximately divided by 100. So can you please calculate the value of IB here, somebody, 200 microampere divided by 100.
2 microamp.
Yeah, 2 microampere. So roughly you can calculate the value of R1 as 10 divided by 2 microampere. It comes very high, right? 5 mega ohm. Yes,
Yes, sir.
it comes to be such a high value, right? 5 mega ohm. This current should this resistance should prevent the sudden inrush of the current to the non-inverting terminal, right? So that is the purpose of your R1 here. Okay, so now after having calculated the value of R1, what else is left in this problem now for us to calculate? Let me make it little small and bring it this side. Yes, so R1 is calculated. Then you have to calculate the value of R2 and R3, right? So your VCC is equals to 12 volts. Okay, so out of R2 and R3, any one value you have to assume R2 to be equal to say 1 kilo ohm or something like that. Now you can calculate the value of R3, right? So V reference is equals to total voltage, that is VCC, into resistance of the same branch divided by total resistance. So here I have this as 2, this as 12, R3 is not known to me, and R2 I have taken it to be 1 kilo ohm plus R3. You please calculate the value of R3. It is as per the voltage divider theorem. Somebody tell me the value of R3. Please calculate the value of R3 and tell me. And for diode, PIV, peak inverse voltage, is plus or minus 24 volts. This we have already seen earlier also. And reverse recovery time, maximum reverse recovery time, it is equal to say T by 2, that is T by 2 is taken to be 0.5 millisecond. You are giving sufficient time for the diode. And load resistance, so the maximum voltage here what can come is 12 volts, correct or not? This is what is the maximum voltage from 0. It can V naught maximum is 12 volts. The current what can flow here is 200 microampere. I maximum can be 200 microampere. I just draw a line here. Okay, so you can find out the value of RL also. RL approximately 12 divided by 200 microampere. This is what is the approximate value of RL. You can definitely select a higher value. Did anyone calculate the value of R3?
200, sir.
200 ohm.
Yes, sir.
Yeah, it is when it is 1K, it should be 200 only, right? Because this here you have got 12 volts and you want 2 volts here. Yes. So what is the value of RL?
60 Q.
60K. Can take this as 60K. This is an approximate calculation.